Yeah, hi folks, this is the next video for Core Pure. We're looking at 7E. As you know, my favourite thing is to draw in 3D. So let's see how this goes. So transformations in 3D. First, I just want to establish a bit of terminology. What I'm doing is, if you imagine me standing in front of the whiteboard, I'm drawing my normal rectangular XY axes, and then I'm taking the whiteboard off the wall, putting it on the floor, and looking at it from above. So this is a representation. There's my X-axis, there's my Y-axis. There's my whiteboard laid on the floor, and the Z-axis is vertically upwards. So they're my three axes, all at 90 degrees to each other. Now, what we normally look at when we deal with 2D axes is the XY plane. The plane, by which I just mean a flat piece of paper, the plane created by the X and Y coordinates. Everywhere on the XY plane, Z equals 0. So the plane where the Z coordinate is 0 is also called the XY plane, and that's just a flat piece of paper flat on the floor. The board that I've just taken off the wall and put on the floor is my XY plane. Of course, X equals 0. Well, if my X coordinate is 0, my piece of paper will be vertical, cutting through the Y-axis parallel to the Z-axis, so that's the YZ plane. And Y equals 0 gives me the XZ plane. So Z equals 0 and the XY plane, they're the same thing. Now, I can represent reflections in those planes in exactly the same way as I can in 2D by considering what happens to those unit vectors. So I consider 1, 0, 0, I consider 0, 1, 0, and I consider 0, 0, 1. In exactly the same way as we consider those unit vectors in 2D. So if I reflect in the XY plane, I'm saying what happens to 1, 0, 0, 0, 1, 0, 0, 0, 1. And not surprisingly, it's the identity matrix because it just makes it convenient for us. Well, I'm reflecting in the XY plane, so the flat piece of paper, the XY plane, clearly red and blue. If you're colourblind, red's the red one, blue's the blue one. Clearly they're not going anywhere. So 1, 0, 0 stays as 1, 0, 0. 0, 1, 0 stays as 0, 1, 0. 0, 0, 1 gets reflected. It's going to reflect in the XY plane. It's going to end up pointing downwards. So it's going to go to 0, 0, minus 1. So that's the matrix that represents a transformation in the XY plane. And of course, I can then apply that matrix to any point that I like. Let's apply it to, well, example 12 says apply it to minus 1, 2, 3. Well, we can see what's going to happen. Remember what we said was the X vector doesn't change, the Y coordinate doesn't change, so I'm going to end up with minus 1, 2, and the Z coordinate will turn into minus 3. So remember, I want the image of a point. I need to write it as coordinates, so I write it as coordinates, minus 1, 2, minus 3. So that's example 12. Now, of course, I could reflect in any plane. So there's a bit of spiel in the book after this that talks about how If I reflect in x equals 0, that turns into -1. If I reflect in y equals 0, that turns into -1. If I reflect in z equals 0, that turns into -1. I don't necessarily need to remember this, but it is fairly obvious if we consider what happens to each of those 3 unit vectors. And the more difficult thing is rotation. Let's draw out the axes again. And z. Okay. Where's my x vector? Y vector and my z vector. Okay, I'm going to rotate about the x-axis. Rotate, let's say, theta anti-clockwise about the x-axis. What that means is I'm standing at the end of the x-axis and I'm looking towards the origin. What's going to happen to these 3 vectors? Well, the x vector isn't going to change. So 1, 0, 0 stays as 1, 0, 0. What I'm going to see is I'm going to see the YZ plane. Let's have a think about what happens to the YZ plane. My Y vector starts there with a length of 1. I'm going to rotate it anti-clockwise. So I'm going to go up to there. Still got a length of 1, an angle of theta, and I need to know what the y component of the y vector is, or the image, and what the z component of the z vector is. Well, remember, this is the z component is the opposite side of my triangle. The horizontal side, if you like, is the y component. So 0, 1, 0, well, nothing's going to happen to the x component of my blue vector. So the x component stays the same. As it happens, the x component of the green stays the same as well. The y component, this bit here, is cos theta. Get mixed up with my colours. And the z component is sine theta. If I think about what happens to the z component after its rotation, well, it starts there and it turns anti-clockwise. I can see that the y component is going to be negative, and it's going to be negative sine theta because it's opposite the angle. And the height, the z component of my transformed vector, is cos theta. Now these 4 here, this is the matrix that you're already given in the formula booklet. This is the 2D matrix for rotation about the origin. So what we're saying is if I rotate anti-clockwise about my x-axis, the x vector isn't going to change. The x components of my 2 y and z vectors aren't going to change. And really this is actually a 2D rotation, and I can just use the matrix that I'm given. I'm going to rotate about the z-axis. So theta about the z-axis, I want to do the same thing. What happens to 1, 0, 0, 0, 1, 0, 0, 0, 1? Well, let's think about what we see. So I'm stood at the end of the z-axis, looking down towards the origin. I'm going to see the xy plane. And the xy plane is just what I've been given in the formula booklet. X, y. Remember, the z vector isn't going to change. So 0, 0, 1. Also, the z components of my blue and red, they're not going to change because I'm just rotating in the xy plane around the z-axis. So the z components don't change. Let's think about what happens to my x vector. It rotates theta anti-clockwise. So the x component is going to be cos theta. The y component is going to be sine theta. And it won't surprise you to know that this is also the 2D rotation matrix, because really that's what we're doing. We're doing a 2D rotation in the xy plane, but also adding on some z components. So those both make sense. Now, rotating about the y-axis is odd. Let's just have a think about it. If I'm stood here and I'm looking down the y-axis towards the origin, I see the xz plane. But for this man looking down the y-axis, the x-axis is actually going to the left. So I need to think about that. If I rotate theta about the y-axis, what am I going to see? I'm going to see a vertical z-axis. I'm going to see an x-axis going off to the left. So the positive direction for the x-axis is the opposite to that which we're used to. So there's my z, there's my x. Just looking at my colour code, I get it different every time. That's where z starts. And x is red. That's where x starts. I'm going to rotate anti-clockwise, and remember it's relative to the man standing at the end of the axis. So anti-clockwise for him. I'm going to rotate anti-clockwise. Well, of course, my y vector isn't going to change, nor the y components of my other two vectors. But what's going to happen to red? Let's think about it. It goes anti-clockwise, theta. So the x component, remember, this direction is now positive, so the x component is going to be cos theta. The z component is negative because it's in the negative z direction, so it's minus sine theta. And let's think about the z component. Well, I rotate it theta. The x component is positive because the positive direction is the opposite now. So that's positive sine theta. And the z component is cos theta. Now this is not the 2x2 matrix that we're given. What we're given in the formula booklet, the 2D 2x2 matrix, is cos theta, sine theta, minus sine theta, cos theta. And you can see here that those two signs have changed. And that's because we're defining the x as the opposite direction because I'm stood at the end of the y-axis. Hang on, dogs are barking. Back in a sec. Okay, I'm back, folks. I was just sorting the dog out. Okay, so let's look at example 13. Now, example 13. Root 3 over 2. So there's a couple of ways of doing this. Whichever way I do it, I recognise that this is a rotation about the y-axis because look, the y vector hasn't changed. So let's be the man stood at the end of the y-axis. Let's be stood here. And remember, I see the xz plane and the positive x direction is the opposite to what I think. So let's draw it. Z, x is going that way, and x has gone from 1, 0 to positive root 3 over 2. Remember, that's the positive direction, minus a half. So it's gone down, let's enlarge it a bit. It's gone down here. So there's my theta. My z component is half in the negative z direction. My horizontal component is root 3 over 2. And I know that that's 1. So it's asking me to describe this. Well, I know it's a rotation, as I say. I just need to know the angle. Well, sine theta, sine is opposite over hypotenuse, sine theta is a half. So theta is either 30 degrees or what? Well, there's my sine graph. Remember, 30 and that one are the same. So it's either 30 or 150. I mean, it's an acute angle. I'm expecting it to be 30. Well, it is 30. But let's check it. Cos theta is root 3 over 2 over 1. And on a cos graph, so I do inverse cos. Well, I know that that's going to be 30 degrees. Remember, on a cos graph, you take it away from 360. So it must be 30 because that's the only value of theta that fits both of those equations. Also, it's clearly an acute angle, it must be 30. So theta is 30. I could have done that using the z vector, and I end up with the same equations. The other way of doing it is recognise that it's a rotation about the y-axis, compare it to the matrix that we already know, and still write down cos theta equals blah, sin theta equals blah. So either way round, we're ending up with these two equations. Now don't worry too much about the extra solutions. I'm sure you'll remember that from GCSE, but as long as you understand how I've got those equations and then solve them. So this is a rotation about the y-axis 30 degrees anti-clockwise. We could just say 30 degrees because the anti-clockwise direction is the positive direction. So you would not lose marks by not saying anti-clockwise. And then they ask us to apply it to a point. Well, that's just, oops, 3 over 2, 0 minus a half. That's just matrix multiplication. And I mean, I'm doing that on a calculator. Multiplied by -1, -2, 1. And I end up with 1 minus root 3 over 2 minus 2 and 1 plus root 3 over 2. But because I'm asked to give that as a position, the position needs to be given as coordinates 1 minus root 3 over 2 minus 2, 1 plus root 3 over 2. Okay, 7E. See how you go with that. We managed to get through the drawing in 3D nightmare. Well done us. I'll see you next time.